זימון זה 3, לא? זימון זה 3?
Actually, I wanted to discuss with you, there was some answers to a questionnaire and they were so confusing that I can't even understand. One of them said I'm teaching too fast, one of them said, and it's easy to lose me, the other was I'm teaching too slow, you're losing attention because it's too slow. Not enough people here to answer what. But what really I'm getting the feeling is that for a lot of people, a lecture in English is an impediment. Well, it's not enough people here, but how many of you feel that would have been much better that the lecture would have been given in Hebrew? Well, in Chinese I can't suggest. So it's 2 out of 5. Don't know what's the meaning of these small fluctuations, but perhaps...
English is my native language. So
yeah, I know.
so I'm also, I really fall into their camp also at this point.
Not only your native... East Coast, USA.
Yes.
Okay, so, well, either we'll have in the next lecture enough people really to ask this question, or I'll just ignore it because there's not enough people interested in answering. Okay, so, in the last lecture, we looked more closely into the meaning of these phonons that we postulated a couple of lectures ago. Said there is a way to measure them, and the way to measure them that we came up with is the heat capacity. So behavior as function of the behavior of the internal energy as function of temperature. So at the end of the day, we had the following behavior. We know that at very low temperatures, it behaves as a power of T to the third. At large temperatures, we just count how many atoms we have there and give each one of them half kDt. And in between we have some extrapolations that Debye worked hard on giving some not so closed form for it. You can find it in any textbook. But for us, the really interesting thing is basically there is a scale Td, which we estimated T Debye, which is the point of crossover from the low temperature to the high temperature behavior. So that gives us some feeling about the phonons. They behave as particles. They seem to follow the behavior we expect from boson statistics. Very good indication. But we can get even more concrete signature of a particle out of these phonons. What is traditionally done everywhere in physics in order to prove that something is a particle? On what do we waste or invest, depending on your point of view, hundreds of billion dollars per machine? Scattering. Exactly. We take particles, we collide them, we see what comes out, and we deduce from it what is the structure of what's going on there, what are the particles. Well, we can do also scattering of phonons. Now, as I said towards the end of the last lecture, if we want to do scattering, we are looking for neutral particles. Why? Because charged particles, when they try to enter the material, collide immediately with the cloud of electrons around each ion there, and they can't penetrate very, very deep. They won't give you a whole picture of what's happening in the bulk of the material. Okay, so good. We have particles that don't have charge. Neutrons, photons. So we can use them. Okay, the most promising one is neutrons. Their mass is somewhat within a factor of 10 or 100 the same mass as the ions in the lattice, and therefore we can expect there some scattering and seeing the behavior of these ions. What is the bad news about neutrons? Exactly. To accelerate a charged particle, it's easy with parentheses, but it's clear how to do it. Put it in a strong voltage, and you'll get it accelerated. So it started from those tiny machines in the 20s and 30s, and nowadays it's several tens of kilometers circumference, and perhaps they'll go on and build 100 kilometers circumference of such a machine. All this won't help anything for neutrons. How can we get neutrons? Okay, one way is just we have all kinds of radioactive materials. Perhaps they spit out neutrons when they decay. Well, some of them do. What's the problem with that?
Chain reaction.
And now take a gram of radium, you're nowhere close to a chain reaction. If that was so simple, the US didn't need a Manhattan Project to start an atomic bomb.
It's not a coherent source.
Well, that might be a problem, but you'll see that we are using actually not coherent sources. Not necessarily coherent. Excuse me? The yield is very low. The amount of neutrons that come out is very small, not very useful in order to characterize the phonons. What instrument do we have that spits out, gives out a lot of neutrons?
Sun.
Yeah, but you don't want and they are using neutron scattering all over. You don't want to have to fly your experiment close to the sun and do something with it. Not a good method. Nuclear reactors. Nuclear pipes. There you have a large amount of uranium. They slowly disintegrate. You have a chain reaction. All you have to do is stick a pipe into your pile, let the neutrons come out, and you get a serious flux of neutrons out of it. So you have a source that gives you a lot of neutrons. Well, actually, any time that you hear nuclear reactors for research purpose, you think, just a moment, research, what kind of research? Sure, building nuclear facilities, nuclear reactors. No. The research is mainly the neutrons that it gives out and using them for neutron scattering. Because nowadays, everything from checking metal fatigue till characterizing all kinds of materials are done on a flux of neutrons. There's the working horse for these kinds of research fields. So anytime you need a nuclear reactor for any shady purpose that you need it, you say, no, 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 I need it for research purposes. I really, really, really want to study phonons. So, okay, we have our source, and actually, just not the course, but just an interesting fact. What other, beyond generation of electricity, what other peaceful use do you have for nuclear reactors?
What else?
Well, that's for not energy production. Something that really use, again, the neutron flux, but not directly. Medical purposes. From directly treating all kinds of tumors with a flux of neutrons, for the same reason. They are not charged, they can go deep into the body, you can concentrate them on a specific region, and if you have things that you can't come in and cut them, let's say some tumor in the brain or some other sensitive areas that you can't just go in and cut it, you can use these neutrons, and you can use them to create radioactive isotopes that are used all over medicine for diagnostics. So a nuclear reactor, we have the feeling that it only either creates energy or some malicious use, but no, it has also some beneficial use from research to medical purposes. Okay, so that was a sideshow. Okay, so what can we do with these neutrons? Well, scatter them. Okay, now almost forgetting about quantum mechanics, if these phonons are particles, what conservation laws should they follow? Momentum and energy. That's the whole game. So, neutron scattering, the mass of the neutron. Someone can give me a rule of thumb times a type of estimation.
10 to the minus 27, something like
you put your yeah, about right. Why?
It's the same mass as the proton.
Exactly, and from where do I know the mass of a proton?
From the hydrogen atom.
The easiest answer is the hydrogen atom. Another answer that you can, it's good to keep in your head all the time, it's around 2,000 times the mass of an electron. That's the reason why when you're doing the spectrum of a hydrogen atom, you don't assume that the nuclear, which in that case is just a proton, moves. You just write a static potential. You really should write some interaction between two particles, but you don't worry so much on that as the same way that you didn't worry about the movement of the sun when you did in high schools the calculation of the period of Earth or Jupiter or heaven knows what you did there. So it's about 10 to the minus 27. Actually, it's, I think it's one. It's written something of the order of 1.67 kilograms. Okay, so as we said, we have two conservation laws that we should keep here, energy and momentum. Okay, so the energy of the system is, or actually let's do it simpler, the energy of the neutron is, in the beginning, is equal to the energy of the neutron after the collision which is, this guy is the change of the number of phonons in the system. Could have collided with one or more phonons, and therefore we have one or more phonons less or more than we had before. And that's what this delta NKS tells us. Okay, so this is energy. Okay, what else do we have? Momentum. Okay, so the momentum of the neutron before the collision the momentum of the phonon of the neutron after the collision. Write it down. The momentum of the phonons that were added or subtracted or lost from the system. And what are we missing here?
Electron decay, no?
We have here the reciprocal vector. lattice vector. Because conservation of momentum is just conservation of quasi-momentum. Okay. Okay, what will happen if it doesn't emit or swallow any phonons? Will something change? Surprisingly, yes. Here, nothing can happen. It came in with some energy. It can come out with some energy. Same energy. But here, right. And what is that? We have encountered this behavior.
With photon scattering.
Right.
It's the exact same equation.
It's just the Bragg scattering. The elastic neutron scattering is exactly the same as elastic photon scattering. Why? Because who cares how I call the particle? And everything that we have learned for X-ray scattering could be relevant here. Now, if we want a deeper physical intuition on what's happening here, because we're not used to a particle hitting nothing and changing its direction, right? Someone can give me a physical picture that will help us to understand what's happening here?
Maybe the phonons change its direction.
No phonons in the game. I came in and out with the same number of phonons in the system. Okay, let's go a step to what we did in photons. Why photons come in one direction and go out in another direction?
They're reflected. Absorbed and emitted.
No, that's not what we did, sir. They interfere. Right? Now we go back to what we have already forgot out of modern physics. As I tell you all over this course, we pull out concepts from everything that you've learned till here. You can treat it as think about it as a wave, as a neutron. It's very small mass, behaves as a wave, it has interference. This is exactly the result of interference as we had for photons. Okay, so the picture is very similar. So, actually, for elastic scattering of neutrons off phonons, we will get also a Bragg peak. It's also a way to characterize the lattice. Since I can control the momentum or the wavelengths or the speed of the neutrons. By the way, how can I do it? Not by inserting a Maxwell denominator that lets only neutrons with a certain speed go through it. Actually, it's a very, very simple contraption. Take two disks that absorb neutrons, put it on a rod, cut openings here and here, and turn it. Only neutrons with a certain velocity, which corresponds to the fact that it went into here and came to here in time to meet the second opening, will get through. So it's very simple technology to control speed of neutrons. Basically something that could have been invented in the 18th century if someone knew what's neutrons.
How to fire them?
Well, and well, we don't know how to fire them also. We just have a large pile of things that spits it out. And perhaps the correct statement is, and had a nuclear reactor. Great. No eraser, I see. Do I have a volunteer to get out and... no, but can someone go to the secretary? This will solve the problem for the next 5 minutes, but not for the rest of the lecture. Right, so zero phonons, we're back to Bragg's scattering. One phonon. Okay, I go to my equations here, but now I have only one phonon. Okay, energy conservation.
Okay, yes, it's not a vector.
Definitely a vector. Okay. Since I can rewrite the energy conservation
This is far from the interaction, right? That's why we can put the energy. Free energy.
Oh, sorry.
And then you plug it in and see
Yeah.
E squared after that.
Completely correct. And so I've just used here for Ks the momentum conservation. I can't write it down as k squared or CSK because I don't know the dispersion relation for a particular phonon. I have to know what is the dispersion relation for this specific phonon that's either absorbed or emitted. And this depends already on the details of the material. The only thing we know out of it is this equation is not easy to fulfill. So you won't have many peaks due to one phonon scattering. You have to have much luck to land on a value of P and P primes that fulfills this relation. Why am I saying a value of P and P prime? Because that exactly defines your scattering. You come with P, you come out with P prime, and does this relation hold? Yes, you have 0 P. No, you don't see anything. Okay, so these are rare peaks. Yeah.
Shouldn't there be a scalar product somewhere? Because these are vectors.
No, this is a function.
Ah, okay.
It's the same function that's here.
Okay.
It depends on the vector. I didn't write its form because it depends on the material. What comes after 1? 2. So let's see what happens for 2 phonons. Or you are now writing the k as a k vector. doesn't have to be on the same branch, this phonon, the second phonon. Doesn't have to be the same K. So that's the energy conservation. The momentum conservation. Prime and prime, again, doesn't have to be on the same K, doesn't have to be on the same branch even. Why the same G? Why not plus G, H bar G plus H bar G prime?
Because
So
the
that's
logic is
it.
the same.
Because summing up two different reciprocal lattice vectors gives you, again, a reciprocal lattice vector, no point in writing down G plus G prime. Okay, so what do I see out of it? Basically, since I have now the freedom to choose both K and K prime, I can always fulfill this relation. So, at the end of the day, what do I get here? If I'm looking on a plot of, let's say, neutron intensity at some and function of difference in energy where I sum up over all directions, the two photon scattering will give me some background, can have some shape, but it's always there, and I'll get some peaks coming out of one phonon scatterings. And looking on these peaks, changing the energy, changing direction, gives me information about the phonons. Same way that if I'm doing high energy physics and colliding two, choose whatever is your favorite elementary particle, I see a lot of things coming out in all directions. I check what do I see, and I can reconstruct it and say, oh, we saw a Higgs. Okay, we can go through the same game with photons. What do I have to remember about photons?
No mass.
Okay, so I won't be able to do this thing. But what can I do there?
H bar K.
Right, I can use this connection, and I can use the momentum of a photon, which is CK. Okay, so I go and do the same game. I can have same results, similar results. Of course, the exact point where I have peaks and I'll have background could be different, but not only could, will be different. But the physics is the same idea. course, we're using particles to scatter off phonons. Details can be different. The idea is the same. The only thing as for names, for photons scattering off acoustic phonons is known as Brillouin scattering. Someone can guess what's the name of scattering of optical phonons? You hear anyone who goes into a seminar in optics or materials and stuff hears it all the time. Raman scattering. Raman, not the noodles, it's an Indian physicist that was the first to see it. And that's a very strong tool to characterize materials. And for practical uses in nonlinear optics, for example. Okay, we're not going into it in this course, but that's the origin, scattering of phonons. Okay, so we spent 4 or 5 weeks on the properties of the lattice. We started with just defining lattices, X-ray scattering of lattices, lattice vibrations, measuring lattice vibrations. Okay, when I'm telling you solid state physics, what's the first thing that comes to mind? Semiconductors, which is basically the electronic properties of these materials, which we didn't say anything till this point. What we are doing from here and the rest of the course is electronic properties of lattices. We'll assume that we have some lattice structure. We know it by X-ray diffraction or by neutron scattering, or someone who checked up in Google and decided that the answer there is correct. We know the structure. Now we want to understand what actually determines the electronic properties. And what are electronic properties? What properties do you know from daily life, I would say even from kindergarten, about solids? Correct? We know that they either are good conductors, most metals, or they're insulators. At the moment, if I'll stop you and ask why this material is a good conductor, this material is a good insulator, you and anyone else that lived before quantum mechanics would stare at me and have no good answer. We will see that it depends on the spectrum, on solving Schrödinger's equation for electrons in a lattice. Basically, that's what determines if a system or material is a conductor or an insulator or a semiconductor, whatever that is. And we'll learn what it is, and I even explain some of the uses as electronic devices. Perhaps we won't get to a transistor, but we definitely will understand how a diode works. That's one aim that we have in this course. The other aim is, what other property do you know about solids? Very important, all your devices would be useless without them, and I'm not talking about electric conductance.
Thermal conductivity.
Yes, but that has to do also with the lattice. We will also discuss thermal conductivity somewhat of electrons, but that's not what I point towards. But he's right. If we have electrons in the system, we have more degrees of freedom. So everything that I calculated, let's say, is the heat capacity of the lattice. I have to ask what the electrons play. Could stop and stare at me and say, well, electrons are so small compared to ions, who cares? But what do we know from thermodynamics?
At each degree of freedom contributes.
Half kT for each degree of freedom. I don't care if this degree of freedom is from a light particle, a heavy particle, whatever. That's the beauty of thermodynamics. It's universal. Half kT for any degree of freedom. So electrons will contribute to the heat capacity of materials. Actually, already in this point, you can stop yourself and ask, why did you waste time on calculating the heat capacity of the lattice? For each ion, how many electrons do I have? Tens, right, for a typical ion. So why waste time on calculating a small contribution to the heat capacity where you have tens of electrons, each of them 6 degrees of freedom, half kT for each one of them? They are determining the heat capacity, not the atoms, not the ions in this game. Well, no. Why no? Because of quantum mechanics. We'll see that most electrons are out of the game.
We only care about the valence vector.
But even in the valence electrons, you can have 2, 3, 4 times more electrons, right? So that's important. Don't waste my time on the lattice. No, actually, very few. No, that's something connected with electric resistivity and electric conductance.
Maybe transparency, how they interact with light.
No. Magnetic properties. You won't have memories without magnetic properties. The good old computers of the end of the 40s and the beginning of 50s that stored information in all kind of complicated contraptions would have left you in a situation that none of your devices would be useful because they would have been large collections of electronic tubes in them that were very fickle. They got bad very quickly, and most important, they were very heavy and bulky. You wouldn't have anything going around. And without a memory, all your devices are basically useless. Magnetic properties. Well, even worse, you couldn't have attached anything to your frigidaire door. So, and again, magnetic properties mainly come out of the electrons. So we have to understand how electrons behave in a lattice. And that will be the main feature of the upcoming lectures. Basically, we will start from some useful observations that were around from the 1850s or 70s or something like that, when people started to play with electricity and conductance, till the point where quantum mechanics came into the game and we started really to understand what's happening to these. So, I don't know, from 2000, 3000 BC, we know that there are metals. We didn't perhaps know that they conduct electricity, but we knew that they are very useful for hitting someone over his head or building a helmet so when he's hit over his head he'll have less of a damage. So metals are around human civilization already for 4,000 or 5,000 years. Actually, if you go back in defining history, you know that ages are defined by what metals were used. The bronze, the iron, the silicon. Although silicon is not exactly a metal, but so and people knew a lot about metals, but mainly about mechanical properties, how to make the steel stronger, less brittle, more elastic, all kinds of games around it, and it was mainly by trial and error. People played around. If something worked well, people copied it and continued with it. If it didn't work, they let it go. Okay, but then electricity appeared and suddenly metals had another property. Well, actually magnetism always fascinated, but somehow from the point of view of scientific research, it was mainly black magic. There's some forces in this thing. Well, let's not be too dismissive of these people. Till today, people will sell you crystals and magnetic things that are supposed to improve whatever people buy them. So nothing much changed. Anyway, in around 1800, we started to understand that there are metals, and metals are usually good conductors. What is the conducting mechanism, and how to explain this behavior? Okay, until 1897, you didn't even have the language to speak about it. What happened in 1897? No, Maxwell equations is 1850. The electron. If you don't know about what is a particle that has charge, whatever you tell us about how metals are constructed and what happens in them is no more than a story around. Actually interesting to note is that Cambridge, in a Cavendish laboratory, where this electron was discovered by Thomson, for many years after the discovery, there was each year a special dinner, and they had a toast there, had a drink, and the things, as I said before, drinking this drink, the toast, was to the discovery of the electron, and may it never be of use to anyone. They are doing basic science. Well, they were completely wrong. It was extremely useful. Okay, so around 1907, Drude came with trying to understand what determines the behavior of a metal, and came up with the following model, which is a model which is basically, I would call it statistical in nature. No quantum mechanics, nothing really to build upon, but some simple observations. Okay, what's the first observation that you have? Metals are you can determine a resistivity. Copper will have more or less the same resistivity, whatever gold will have another, silver will have another. Truth is that it depends on purity and all kinds of things, but very broadly speaking, it's a material property. And what else do we know about resistivity?
Ohm's law.
Yes, that's Ohm's law. You take a number and stick it there as the resistivity of the conductor. But physical.
Generates heat.
Right. We know that we have heat generation. And we know that we won't have an electric current unless we put a potential on it, an electric field. So if you have a conductor, what this picture is, it's some kind of lattice. So we have ions in it. So you have some positive core or nucleus of this material. You have most of the electrons remain around these ions, but you have some free electrons. That's the new concept. Okay, so some of the electrons are somehow detached from these atoms. You put an electric field. So if you had just electrons in free space and you put an electric field, they will accelerate and reach whatever velocities that you have. Let's not worry for a moment about relativity. Just you can pump more and more energy into it, so current is not limited. But these electrons go around, hit an ion, move it, create phonons, that is emitted as heat, and then start again. And we have basically, what are you calling such a model from statistical mechanics? I think you have ran into it. Exactly. A random walk of electrons in this material. Have a diffusion of these electrons. So they get to some steady velocity. They have a steady heat output because they transfer the energies that they have gained out of the electric field to the ions. And that's that. That's the physical picture. Now, what is missing here? A few things. One of them, how many electrons do I have in a gram or in a piece of metal? It's not just a number of atoms times, don't know what, 1, 2, 3, 4, that wouldn't have worked. So you have here number or since I want something that will work for 1 gram of metal or 2 gram or 100 gram, I'll talk about density of electrons. If I'm very naive, I would say that the Ne some valence of the number of electrons times the number of atoms. How many electrons do I have in the outer shell times the number of atoms. This didn't work from the beginning, so it was dropped very quickly. So
the ions have more charge and they need to get in a stationary state, like the minimum energy, and they look
no, but that you can answer. Let's say if you smear a negative charge around the positive ions, their influence will be quite small, so the energy stored is not terrible. If you're moving all the electrons to the second part of the room, you're in problem. So the fact that the electrons are free here it's still a neutral piece of metal. We know actually very well that trying to add or remove charge from a capacitor costs you a lot of energy. So it's not that you have more electrons than the charge of the nucleus. No, you have the same number.
But you can lose more energy, right? Mobility of electrons.
Oh, let's not put in terms that we haven't yet defined. We will define mobility. It's an important concept. Okay, another important concept is okay, it doesn't necessarily connect with the distance between ions or the distance between lattice points, because, as I said, I'm not so sure that each that the proportion between the number of electrons and the number of atoms is necessarily just the number of valence electrons in each atom. So this is Rs. Okay, a very rough estimation. So Rs and the natural length scales that I compare it to what's happening in atoms usually is the Bohr radius. So I expect that Rs will be of the order of a few angstroms. Okay, so what do I need in order to turn this cartoon into some kind of physical models that can give me predictions? Well, I have to assume something about what's happening in these collisions between the atoms and the ions, between the electrons and the ions, and the assumptions are the most basic and most trivial assumptions. So the electrons gain their energy out of the acceleration of the electric field. They hit an ion. They transfer all their energy to the ion. They come out in some random direction and they are accelerated again. So what controls this process? As usual in random walk and such statistical mechanics behaviors, the rates of collision, right? How much time comes between each collision? So tau is the time between collisions, 1 over tau is the rate of collisions. How many collisions do I have for a given time? Okay. What else do we know about metals? Ohm's law. Sorry that it's the same. Okay, I've noted the volume with 2 lines above it, so this is the voltage. Yeah, I hope this is familiar to you. Okay. I want to rewrite it in a different way. Sorry for returning you to the 11th grade, but why is this true?
Because electric field is the gradient of the potential.
What? If you want to know the potential, it's the fields that you worked against times the distance that you worked. All the time I'm saying worked. Work is force times distance that I do this way. Okay, not to confuse us, we'll go here. Again, high school physics, let's call A the area through which the electrons flow. Is the size. J is the current density, current per unit area. So this is IJA, and the resistivity, as you should have known, is just the resistivity of the material, which depends on whatever it depends on, times L, just adding a longer resistor makes it more resistive. R grows, making it wider reduces. If it's not clear, adding resistors in consecutively makes the resistance higher, adding them parallel makes the resistance smaller. Okay, so that's all that's written here. So, manipulating both sides gives me again, high school physics. J density of electrons times the charge of an electron times the velocity of the electron, and the minus you can attribute to whomever decided that charge of the electron is negative. Okay, all that is again, manipulation of terms. 1 over the resistivity is the conductance. Okay, I can write it down also from the definition of rho. And here I was a bit more careful not writing down the velocity of any electron, but the average value of the velocity. How did I get that relation? Well, I did simple Newtonian mechanics. Right? If I measured the velocity of the electron as v0 at some point, after time t, it's a times t. Come on, 10th grade physics. Why is this a? Because a is f over m. F is this guy, m is this guy, that's all. Now we do statistical mechanics, or level 0 statistical mechanics. Just put the average sign on whatever can be average, not the electric field, not the mass, not the electron charge, all the rest. Let's start immediately after the collision. We said that it comes out in any direction, so V0 average is 0. How much time does it have to acquire velocity till the next collision? So it will be E. Stick it here, get this. Lo and behold, after doing 10th grade physics, you get Drude's definition of conductance. Well, at this point, not extremely useful. Why? E, I can measure independently. M of the electron if I would have been in 1907, I would believe that I can measure independently. Within 2 or 3 lectures, you will understand why that statement is not correct. Actually, the mass of the electron in a lattice is not equal to the mass of the electron outside of the lattice. But we're in 1907, life is simple, and we believe that we know the mass of the electron. But I don't know what is the number of electrons, or if I would have believed that I know the number of electrons participating in this game according to the number of electrons in the valence of each atom, wouldn't be correct, and I have no clue how to pull out tau. So if I decide that I know this guy, and this guy, which at least for 2 of them I have some caveats, I believe that that's the way to pull out tau, but it doesn't prove the Drude. It just creates a connection. You want to measure tau, measure the conductance, and you'll have some estimate on tau. Okay, so what do you do in such a situation? I have a measurement that, one measurement that gives me one parameter. And basically it just translates one thing to the other. It doesn't prove that you measured this parameter. What do you do in such a situation?
Another measurement.
You need to do another independent measurement that will give you this tau. Then you can compare them, and if they're equal, you said something meaningful. Not just some translation of one unknown to another unknown. Okay, what kind of measurements can you do to the conductance that will give you tau? Fortunately, there is an effect that people knew already at that time, which is something that, again, you have run into in high school. The Hall effect. Putting a magnetic field will screw up, I've erased already the picture, will change the trajectories of the electrons and create voltage in the y direction, not only in the direction of the field, but also perpendicular. We can measure that voltage and get another input on what's going on. Okay, so we have to describe what do we expect to get from this Hall measurement, and see what happens in experiment. And there we will run headlong into something that makes no sense at all. Meaning that we'll end up with the conclusion that in some metals, not all of them, not only the numbers don't fit, we get electrons with charge carriers which have positive charge, which is extremely strange. So what we will do in the next lecture is define how do we calculate the Hall effect. We will classically compare the results and understand that we have to move to a quantum solution and see what do we get there. Okay, so tomorrow.